Hello, I am Rowan Al-Harbi from Northwestern Habits Lab, presenting our work HeatSight, enabling wearable low-power omni-thermal sensing. Thermal infrared is naturally emitted by objects around us, including humans. Similar to RGB and depth cameras, thermal sensors capture both spatial and temporal information, providing us with a less obtrusive opportunity to understand and identify personal activities. While RGB information is lost, unlike RGB-based cameras, thermal sensing is not affected by scene illumination. A thermal image obtained in the dark will look similar to an image captured in a well-lit environment, allowing us to capture human activity in different contexts. Thermal sensors do not require color contrast between the object and the background, which reduces the potential of algorithmic bias due to skin color differences. It is also robust to occlusion from many materials, reducing noise and unnecessary information, which simplify the machine learning tasks. Thermal sensors can be covered with opaque materials to increase the wearability of the device and minimize stigma and discomfort while still maintaining utility. However, the high battery requirement of traditional thermal camera systems and its narrow field of view remain an open research challenge, affecting the wearability and the utility of thermal sensors for human activity recognition. This work presents HeatSight, a wearable low-power omni-thermal sensing system with a wide field of view that captures the wearer body and surrounding objects. HeatSight comprises 5 thermal sensors in a pentrahedron configuration to increase field of view, allowing for a capture of a wider range of egocentric activities. We designed and 3D printed a case to encapsulate HeatSight. The case contained a base that holds the sensors at the desired angle to achieve a 180 degrees field of view. The system is worn on the body using a neck strap and strong magnets clasping onto the wearer's garments to ensure correct positioning. A thermal passing opaque material then covers the sensors. To reduce energy consumption, we used low-resolution thermal sensors. Each thermal sensor captured an 8 by 8 thermal image, which then we combined to produce a 24 by 24 thermal image. The data acquisition and storage is handled by an ultra-low power microcontroller. HeatSight can capture the wearer's frontal body and their surrounding objects, providing a rich stream of thermal, temporal, and spatial information for human activity recognition models. We use a two-layer CNN network to build a human activity recognition model using data obtained from HeatSight. To model the temporal information, we use a 3.5-second window by stacking 35 consecutive frames as input. To assess HeatSight feasibility in classifying human activity, we conducted an in-lab experiment with 6 participants, in which they performed 14 daily life activities that are of interest to the wearable research community. Participants performed the complete set of their activities in the lab once per round. They were asked to perform each activity for at least 15 seconds. In total, participants performed 3 rounds. This confusion matrix shows the result after training our models with data obtained from 2 rounds and testing it on 1 round. As we can see, activities involving objects with distinctive thermal signature, such as drinking a cold beverage or smoking, have a high score, showing the benefit of thermal signatures. Even when the activity does not involve an object with a thermal signature, such as socializing or brushing one's teeth, thermal sensors capture spatial and temporal information from the wearer hands that help in distinguishing between such activities. Activities that do not contain enough thermal, spatial, and temporal information, for example, drinking and eating something at room temperature, are highly confounded activities that are hard to model using limited dataset. We believe that by collecting more data, we can improve the results of detecting such activities. In this work, we presented HeatSight, a wearable system that captures the thermal environment of the wearer and uses machine learning to infer human activity from thermal, spatial, and temporal information in that environment. With HeatSight, we unlock thermal as an egocentric modality for future interaction research. For more information, please visit our website, heatsight.info. Thank you.